Hi, I'm Mark Barsamian. In this video, I'll be discussing the closed interval method for finding absolute extrema for a continuous function on a closed interval. This material is from section 4.5 of the book. More specifically, pages 298 and 299, example 1, is similar to what I'm going to be discussing. And the corresponding homework is this set of two exercises from section 4.5. Now recall the definition of critical numbers from section 4.1, which I discussed in the video for homework 55. A critical number for a function f of x is an x value, x equals c, that satisfies two requirements. The first requirement is that the number must be a partition number for f prime of x, and the second requirement is that the number must be in the domain of f of x. That is, f prime parentheses c equals 0, or f prime parentheses c does not exist, and f of c exists. And recall the definition of absolute extrema from section 4.5, which was discussed in the previous video for homework 61. An absolute max for a function is a y value, f parentheses c, with the property that it's the greatest y value for all x in the domain of the function. In other words, if you compare f of c to f of x for any x in the domain of the function, f of c is greater than or equal to f of x. An absolute min is the same sort of thing, but f of c is the least y value for all x's in the domain. So if you compare f of c to f of x for any x in the domain of f, then f of c is less than or equal to f of x. In the previous video, we discussed this extended example where we had a graph of a function f of x, and we considered different intervals on that graph, and we looked for local maxes, local mins, absolute maxes, and absolute mins in those intervals. We found, for instance, for this blue interval that's on the graph, that part of the graph with its endpoints, there were local maxes and there were local mins. We found that for this interval, from 6 to 15, but not including the endpoints, we found that on that interval, there were still local maxes and mins, but there was not an absolute max. And so on for these other intervals. So we found that the existence and the values of local and absolute maxes depended on the intervals that you chose. And of course, in some of the intervals, there were no absolute extrema, and in a lot of the intervals, something was missing. Either a local max or min was missing, or maybe an absolute max or min was missing. But there was one important situation where some extrema are guaranteed to occur. That was these two examples had absolute maxes and absolute min, and those two intervals were closed intervals. So we have this theorem, the extreme value theorem, that says if your function f is continuous on a domain that's a closed interval, then it will have both an absolute max and an absolute min on that interval. So these two intervals are closed intervals. The function is continuous on those intervals, and on those intervals, there are both absolute maxes and absolute mins. And also, remember that local extrema can only occur at critical numbers, not at endpoints. So, for instance, for this closed interval, there were no local maxes or local mins because the highest and lowest points on that interval are at the endpoints, and there are no other candidates for local maxes or mins. But absolute max and mins can occur at endpoints. And so we have this second theorem that says absolute extrema, if they exist, must occur at x values that are either critical numbers or at endpoints. So if you go back up and look at this graph, in all the intervals where there was an absolute max or an absolute min in the interval, every time that happened, those maxes and mins occurred at x values that were either endpoints of the interval or critical numbers. So for instance, this interval, the absolute max occurs at this endpoint. The absolute min occurs at this critical number. Well, those theorems, Theorem 1 and 2, are the basis for the following procedure for finding absolute extrema on a closed interval for a function that's continuous on that interval. It's called the closed interval method. So it's this 5-step process. First of all, you check to make sure that you do have a closed interval and that your function is continuous. And then you find the critical numbers of the function that are in the interval. And then you evaluate f at the endpoints and the critical numbers. Now, evaluate f means you just simply find the y values. So to say evaluate f at c means simply find f parentheses c, that is, find the y value. And then you end up with a list of y values from doing this step 3. You find the y value at the endpoint A. You find the y value at the endpoint B. You find the y values at all the x values that are critical numbers. You're going to have a list of y values. Well, then you scrutinize that list, and the absolute max will just simply be the largest of those y values, and the absolute min will be the smallest of those y values. So for our first example, we'll find the absolute extrema of this function on this interval. So let's go back up and look at our procedure. Procedure 1 is to check to make sure that your function is continuous and that you do have a closed interval. So we note that the domain is a closed interval, and we note that the function is continuous on the domain, and we say why. We know that it's continuous because it's a polynomial. All right, step 2, we find the critical numbers in the interval. Now remember what the critical numbers are. Critical number is an x value where f prime is 0 or f prime does not exist, and where f of x does exist. There are our critical numbers for f of x equals -1 and x equals 3. The procedure we use to find those is the standard thing. We found f prime of x. It was this polynomial, which could be factored this way. Then we found the x values that cause f prime to be 0. And there are no x values that cause f prime to not exist because f prime is a polynomial. So that gave us these two x values that qualify to be called partition numbers for f prime. Now, then we had to check to make sure that they could qualify to be critical numbers for f of x. That means they had to have this additional qualification. We had to know that f of x exists at those x values. But f of x is a polynomial, so f of x always exists. So those two numbers that were partition numbers for f prime certainly qualify to be called critical numbers for f of x. So we've done step 2. Step 2 was to find the critical numbers in the interval. Well, both of those numbers are in our interval. So step 3, our job is to evaluate f at the endpoints and at the critical numbers. The way I like to do this is I like to make a list of all the important x values. So there's our list of important x values. Now remember what we're supposed to do. We're supposed to evaluate f at the endpoints and at those critical numbers. In other words, we're supposed to find the y values at those x values. So I just make a little table with the important x values in the left column and the corresponding y value in the right column. So there is our list of corresponding y values. I'm not going to show the details of these calculations. It's just arithmetic. That's prerequisite to a course like this. But there are the y values. So there is step 3. We've done step 1. We made sure our function was continuous. We've done step 2. We found the critical numbers. Step 3, we made the list of important x values, that is the endpoints and the critical numbers, and we evaluated the function at those important x values. That is, we found the corresponding y values. Now, basically, we wrap it up. We simply observe the largest value on that list of y values, and we identify that as the max, and then we observe the smallest y value on that list of y values, and we identify that as the min. Well, notice that the greatest y value on this list is 18. And the least y value on this list is minus 14. So there's the result of our step 4 and 5. We identified the greatest y value as the absolute max, and we write these concluding sentences. We say the absolute max is this y value, and we say where it occurs. It occurs at these x values. So these sentences make it clear that the max is a y value. The min is a y value. A couple of observations about the stuff that we just did. First of all, use the formula for f of x to compute the y values. These computations used the formula for f of x, not f prime. We're trying to find y values on the graph of f of x, so we use the formula for f of x. Also notice that absolute extrema can occur at more than one x value. The absolute max was y equals 18. There are not two absolute maxes. There's just one. It's this number, y equals 18. It occurs at two x values. Also note that absolute extrema can occur at critical numbers and at endpoints. This absolute max occurred at an endpoint, also it occurred at a critical number, but the absolute min occurred just at a critical number. Also note this very important thing. The closed interval method does not use a sign chart for f prime to locate the extrema. The absolute extrema must occur at the important x values on the list. We know exactly where the extrema has to occur. The extrema have to occur at those x values. So a sign chart for f prime is not needed. So don't waste time making one. Let's go on. Question B. Find the absolute extrema of the same function on the interval -2, 2. So we already know the critical numbers. There are x equals -1 and x equals 3. But for this question B, with this interval, this critical number is not in our interval. So we're not interested in that critical number anymore. So now let's make our list of important x values. And put a column next to it for the corresponding y values. So there's our list of corresponding y values. So here we've done so far steps 1, 2, and 3. We already knew that our function was continuous. We already knew the critical numbers. and we made our list of important x values, and we found the corresponding y values. So that stuff is done. Now we simply make our conclusions. We identify the greatest y value on that list, identify it as the max, and we identify the smallest y value on the list and identify it as the min, in sentences. So there's our conclusion. 2 sentences. Again, you say what the absolute max is, you label it as a y value, and then you have another sentence that says where it occurs. It occurs at certain x values. Observations about this calculation that we've just done. The absolute extrema depend on the choice of interval. If you change the interval, then the absolute extrema can change. The other thing that's important is the list of important x values does not include critical numbers outside the interval. So we did not include this critical number, x equals 3, because it was not in our interval. So that critical number did not make our list of important x values. Let's go on. This is a little bit harder example. In this example, we have f of x is this 4th degree polynomial, and we're supposed to find the absolute extrema of f of x on this interval minus 2, 3. All right, well, step 1, we observe that our function is continuous on a closed interval. Step 2, we're going to find the critical numbers. So we are looking for critical numbers for the function f of x. Now, as in the previous example, f is a polynomial, so its y values always exist. F prime is also a polynomial, so its values always exist. So there are no x values that cause f prime to not exist. There are some x values that cause f prime to be 0. That's those x values. So those are the only numbers that can be partition numbers for f prime, and they're automatically critical numbers for f of x because they're numbers where we know that f of x exists, because f of x is a polynomial. F of x always exists. So we've done step 2. Now in step 3, we make a list of all the important x values and find the corresponding y values. We'll do that on the next page. So there's our list of important x values. Now we make a column next to it for the corresponding y values. So there's our list of y values. Now again, I did not show all the grungy calculations. That's arithmetic. That's prerequisite for this course. So that's step 3. We evaluated f at the endpoints. Now all that remains is to do our conclusions. Identify the greatest y value and write up a conclusion that identifies it as the max. And similarly for the least value, the least y value being the min. So there's our conclusion. The absolute max is y equals 36. it occurs at two x values, x equals negative square root of 3 and x equals square root of 3. The absolute min is y equals 0. It occurs at x equals 3. Observations about this example. Absolute extrema can occur at x values that are not integers. Our absolute max occurred at these x values that are not integers. Now consider Anne's solution to the question posed in this example. Remember the question was this: find the absolute extrema of that function on the interval -2, 3. So Anne made a list of y values. She made this list of a bunch of x values, and she found the corresponding y values. She observed the greatest y value was that one. It occurs at those two x values. She observed the least y value was that one. It occurs at that x value. So what do you think of her work? Well, notice that Anne got the wrong absolute max. Her absolute max is y equals 35. We know the absolute max is y equals 36. And the reason that happened is she only considered integer x values. So that's why she missed the absolute max. She got the wrong absolute max because she made this list of x values and they were just integers. She just chose all the integers in that interval, and she made that list of integer x values in that interval. Now, Anne happened to get the right value for the absolute min. She got the absolute min of y equals 0. That is the absolute min. Good for Anne. But the thing is, her method does not actually prove that y equals 0 is the absolute min, because she did not investigate the critical numbers. In other words, Anne's answer about the absolute min, an answer that happens to be correct, is no more valid than her answer about the absolute max, that answer that happens to be incorrect. That is, the method that Anne used is an invalid method, even if it may happen to give the correct answer in some situations. Even though it involved a lot of work, Anne did a lot of work here, very impressive how much work she was willing to do, that work is not a valid method for finding absolute extrema. So to find absolute extrema, you have to find the critical numbers. You have to find the critical numbers of the function. You have to make a list of important x values that includes the critical numbers. Oops, I've got a mistake here. This should say endpoint. So again, Anne's method is an invalid method, so we should actually cross it out. Let's go on. Consider Bob's solution to the question. So the question again is find the absolute extrema of that polynomial on that interval. So Bob found the partition numbers for f prime. So the partition numbers are negative square root of 3 and 0 and square root of 3. Then Bob made a sign chart for f prime. So he put the partition numbers on a number line, and then he did all these sign calculations and put the sign information on the number line. So that's the sign chart for f prime. And then Bob said there's a max at x equals negative square root of 3 and also at x equals 3 because that's where the derivative changes from positive to 0 to negative and positive to 0 to negative. And Bob said there's a min at x equals 0 because that's where the derivative changes from negative to 0 to positive. And so then Bob computed the y values at those x values, and Bob found this. Bob found the absolute max was the number 36, and Bob found that the absolute min was the number 27. Well, what do you think of Bob's work? Well, notice that Bob got the wrong absolute min. Bob got an absolute min of 27. We know the absolute min is 0. It occurs at the endpoint, x equals 3. So Bob got the wrong absolute min, and it's because he did not investigate the endpoints. Bob only looked at the critical numbers. So he got the wrong absolute min because the absolute min actually happens to occur at an endpoint, not at a critical number. Now Bob did happen to get the right value for the absolute max. Look, Bob got the absolute max of 36. It happens to happen at one of the critical numbers. But his method does not actually prove that 36 is the absolute max because he did not investigate the endpoints. So in other words, Bob's answer about the absolute max, that answer that happens to be correct, is no more valid than his answer about the absolute min, an answer that happens to be incorrect. That is, the method that he used is an invalid method, even if it may happen to give the correct answer in some situations. So even though it involved a lot of work, it's not a valid method. Now, think about this. All the work that Bob did in making the sign chart for f prime is unnecessary. All that you need is to find the absolute maxes and mins. All you need is this list of important x values and the corresponding list of y values. You don't need to make a sign chart for f prime. Remember, I mentioned that after our first example. I said the closed interval method does not use a sign chart for f prime to locate the extrema. So a sign chart for f prime is not needed, so don't waste your time making one. If you go down and look at all the work that Bob did, he spent all that time making a sign chart, and then he got the wrong value for the absolute min because he forgot to investigate the endpoints. And the thing is, he didn't need this sign chart at all. Even though it's an impressive sign chart, took a lot of work, he didn't need it. So again, don't make a sign chart for f prime when you're doing the closed interval method. That's the end of that example, and that's the end of the video. Thank you.